floor is yours.
Thank you, Michael. I think I'll not take much time. I'll go directly to the point. We know about rare earth element. I think this is one of the demanding element, and the primary source is getting down. So we started thinking about secondary or an alternative sources. So this work has conducted by my PhD student Shondeep, and this project has funded by CSL, Warren and Noshara. They are from CSL. I think there are a number of secondary sources we have. For example, fly ash, seawater, and the mining waste is one of them. So we collected. If we talk about the little bit about mine site in Australia, we have around 95,000 hard rock mine site in Australia all over, and around 90% of them are inactive. And there are a lot of mine sites have tailing facilities, and this tailing facility is one of the source of pollution as well. And sometimes we know that it takes $1 million for a site, rehabilitation or management. So, and we also found that the literature has suggested some of the TSF contain critical minerals and can potentially be recovered for economic and economical benefit. Even in some cases, some of the TSF have higher concentration of rare earth element compared to the primary deposit one. At the same time, because my talk is all about rare earth recovery from mining waste, but I want to talk in details what we have done for this project. At the same time, not all TSF contain critical minerals, so therefore all does not have the same environmental impact. So therefore, if we can have a database about all Australian mining, that would be good to understand which tailing has potential of TSF and potential of rare earth element. So this we collaborated with CSR. We got data from them and from different sources. And with visual inspection, we developed the database, and this is kind of one of the first of its kind in Australia, like in terms of tailing storage facility database. And this database, if we talk about the summary of this TSF database, we found that around 13,000 active sites and 84 are inactive, and total of around 1,100 TSF are identified with only that we have only the TSF. As we said, that not all mining has the TSF facilities, and out of them 103 TSF in Australia, they have the potential with real element. So, and this is like a video tour of TSF database, how we develop using Google Earth. I think if we talk about one of the sites, for example, New South Wales, just if you go to the Google Earth and then it will show that what type of commodity we have in that mine site. Just will show it here. For example, is one of the sites in New South Wales. Maybe site 1, here the major commodities gold, copper, zinc, and lead. The similar way, maybe I'll show another active site in New South Wales. So it has a major commodity of gold. I think understanding this major commodity in tailing sample, then we can come up with, okay, can we really think about recovering some things from that specific mining, and what type of things we need to consider in terms of the recovery. Okay, then based on the database, we collected sample from 2 different mining in Australia from the tailing sample. One of them, I don't want to tell the name because this is still confidential, I think. This tailing sample has a high grade of rare earth, and one of the highest grade rare earth deposit in the world, we can say as well. And this is produced the rare earth concentrate. And when we have done some physiochemical characteristics, we understand that it has, the tailing is dry and has 13% of volatile organic materials. And other things we find out, because when we talk about recovery, so the particle size is very important, and 50% of the particle was less than 61.3 micron. So then we have done other characteristics like a geochemical characteristics, and the major mineral was graphite and the monazite, and the major element was was iron. Iron was kind of considered as an impurity, and we want to consider the rare earth element recovery. If we talk about the rare earth one, I think that it is that there are two types of it. One is light, another one is heavy. This tailings sample has light rare earth element, and we have a more concentration of cerium and lanthanum than the others. So, and we have done some different types of trace analysis and characterization and mineralogical characteristics as well. So as we said that most rare earth element grains are mined around by the iron, and if we look at these mineralogical characteristics, and because of fine grained, as we said, like less than 61 micron, more than 50% of the sample. So we thought maybe if hydrometeorological route can be a good way to recover the rare earth element. And then we tried to listen with hydrochloric acid, and then we found that that is not effective and non-selective, because here some 89% of rare earth recovery, but 100% iron dissolution, and then we used sodium hydroxide followed by hydrochloric acid. And here the rare earth recovery was increased. Again, the iron was a problem, and then selective removal of impurities, particularly iron, was necessary. And then we tried to do some work on how we can separate iron from the rare earth recovery. From this sample, somehow in the main the treated sample, we have only rare earth from the iron. And the main then the next work was to try to work with pH control and temperature control. And after doing that one at different pH and different temperature, and then we understand that almost 100% of particularly more than 97% of iron we are able to separate on the rare earth one. And here the sample, and here if we talk about the mass loss, because when we are separating iron from the sample, only 0.22% of rare earth lost, I think. So this is the work, and here in principle, I think we can say that iron impurity removal mechanism was almost pH dependent, and precipitate has around 96% of iron, and so that we can say that high grade of rare earth recovery was possible here. In principle, if we talk about the conclusion, and then rare earth recovered from iron rich maintaining sample, and precipitate was around 97% of iron, and then means like rest of the sample was rare earth recovery. So our next target to work on how we can selectively recover each of the rare earth element that we have from the sample that we are currently working on. And this is the references, and thanks CSL and RMIT for funding the project.
Thank you very much. Thanks, Will. Very, very important work, so thanks for the nice talk. We've got time for questions from the floor. Actually, you did very well with time, so you've got plenty of time for questions.
That's very good, yeah.
Yep, Andrea.
Thanks, Will. Very, very nice talk. I was wondering, clearly your study shows that, it holds great promise, right, for the recovery of the rare earth metals. So I was wondering, are there any particular, economical barriers or technological barriers to, scale up or maybe apply to a broader scale this process?
Look, I think, as we said, that we have been working with CSL, and we do have a lot of results, but we cannot show it yet.
Okay.
And we do have a plan. I think CSL and Linus, I think we are working with them for this work. I think there is a possibility of, we are thinking for the next stage, pilot scale of this one, because as I said that we have a number of results, and based on the results we're thinking about the next stage. And I think the way we found from our preliminary work and the lab as well, if we close to in the pilot scale, maybe they have a plan to utilize this concept to utilize in their mine site.
Okay.
Because they have 1 million ton of tailings sample, and managing them is an issue. At the same time, they really don't want to utilize the acid and other things. If something like alternative, that would be good. Then biolysing can be another option, but they are not really keen to go through that direction. Maybe can be a good one, but then selective recovery and another thing. considering they are doing maybe, they think still if we can come up with something, acid leaching and other things would be good if we can reuse acid again and again, and our work is going to that direction.
Okay. Thank you.
Yeah.
Thanks. Question?
Thank you, really interesting. I was wondering whether the work that you've done on the database, whether you've been able to or thought about connecting with others who are looking at alternative mine rehabilitation techniques that might be applicable for other mines. You've got a specific focus, but as you noted, it's quite a narrow pool that you're targeting. But the database itself feels like a really useful asset.
I think it's a good point, and I think we are planning to extend this database. For example, here we have only the major commodity. We don't know how much volume and what other things we have in the mine site. And this is still like a hard copy kind of. So we do have to extend this database with considering all these aspects and transfer to a web-based platform, and that would be a huge contribution, I think. And this is one of our work. I mean, the next work is discussing with the industry department.
And so that's great. And just I guess one other thought on the back of it is the extent to which there's an opportunity to feed into government to help their understanding around the nature of the challenge. Because it feels, as you said, that didn't exist before.
Yes,
So
yes. And we have been talking with Australian Geoscience to develop that one as well. I think we are in discussion with how we can make a bigger one. I think considering all these parameters we have, including the volume of different elements, and if we can transfer to the web-based platform, that would be a huge asset for, I think, overall Australia, so that everyone can go and see what is happening for the specific mine site.
Great, thank you.
Yeah.
You're just following on from that. Does that database include like this certain elements in the estimated amount of those elements in each of those sites, so you kind of got an idea of how much potential is in the waste?
That we don't have exactly, but we do have some information from Australian Geoscience and maybe from CSL, because they have been working out there for a long time. So we can have some estimation. And those are based on the estimation, based on the dimension and other things, we can come up with close to that amount.
Yeah.
And maybe we are planning to, add those information to the next database.
Yeah. Because I sort of wonder, these are very much sort of business driven.
Yes.
To sort of try to take the waste. It's like Andrea's question, what are the barriers? Like the mining site will just do what they can.
Yes.
They'll put the waste there because it's not profitable to take any more out of. So what's the incentive? If there's an incentive that says, okay, collectively there's enough volume here to justify a business case to then go and extract it.
Yes.
That might help overcome barriers. Yeah.
So I think Australian Geoscience and CSL, they have been talking on behalf of us, and they have the similar way of, like utilizing those and developing those kind of things, so that can help to them to think about, rather than taking as a problem, like if we can recover things, something, maybe from business point of view, they would like to do that one as well.
That's right. Yeah. If it's not driven by environmental reasons, by business reasons, that makes a huge difference.
Yes, and this is the plan.
Yeah.
Somehow we need to show, for example, only one mine site, they come up with, okay, how we can recover this one, and then if we can do that one, maybe they have the interest, definitely, but we need to come up with, as you said, the business point of view, how that is economically feasible for them.
That's right. Yeah. So the environment needs as well.
Yes.
At the same time.
Yeah.
Does anyone have any more questions? Are we going? We could probably wrap up now unless there's another burning question. No? Okay. Please join me in thanking people for the nice talk and good luck with your work. Okay, so now we can move to our next speaker, Young Woo Chu. Going back to UTS again. Yes, good to see you, Young Woo. Who's going to talk on selective separation and recovery of rare earth elements using electrochemical methods. So, please, the floor is yours, sir.
Hi, good morning. My name is Young Woo. I'm a Chancellor Research Fellow in UTS. I'm very glad to see a lot of rare earth recovery talks this morning, including Dr. Kutluk's, and following to my talk, there will be a chance to talk about the absorption of the rare earth elements. Today I'm going to talk about the selective separation and recovery of the rare earth elements. The title has been slightly changed. It's electric field-driven memory processes. So the rare earth elements, it's critical minerals for cutting-edge technologies, and usually is commonly defined as 17 heavy metal elements, including lanthanides, and they are called vitamins of industry because of their very unique physical and chemical properties.